Okay, so today we're going to take what we learned about sound in the last lesson and apply it to musical instruments. So we're going to, just look at an application of this, and I think that would be good. So let's start with this. What an instrument does is it creates sound, and it creates sound of specific frequencies. You want it to play the note that you're trying to make, because if it made random notes, then you wouldn't be very good at making music. So let's start with this. Which characteristic of a sound wave relates to pitch? This is from the last lesson, and I'm hoping you maybe kind of remember that it is frequency. So what a good instrument does is it can play different frequencies of sound, and it can enable you to adjust the frequency that it produces, because you wouldn't want an instrument that only makes one note. Like, you should be able to play multiple notes to create some sort of song. Now, the equation that sort of determines the frequency of a sound wave is this one. F equals V over lambda. Now, V stands for the speed or velocity. Now, for us, typically you play your instruments in air, like unless you're playing, the underwater tuba or something like that, which we'll measure in meters. So for us, the speed is really mostly always going to be 340 meters per second, which is the speed of sound in air. And I just pulled that from our last lesson. So that's just kind of how fast sound moves in air. Okay, we've also got this lambda, which I just mentioned really quickly last time, is the wavelength. It's a length, so we're going to measure that one in meters. And then we've got F, which stands for the frequency. And you may remember that we measure that in a unit called hertz, Hz, which just represents the number of vibrations or sound waves that reach you per second. So we've got these two different things. We've got V and we've got lambda. By adjusting the speed of the vibrations either in the instrument or in the air, and by adjusting the wavelength, we can change the frequency. So we can make a few changes to what's going on here. We can increase or decrease the wavelength. So if you're good with your math, you might recognize that increasing the wavelength, so if you increase the denominator of a value, or the bottom of the fraction, would decrease the frequency. And remember, decreasing frequency means a lower note. So if you have like a long wave, picture like a long, large instrument, you will have a low frequency. Think of some of the larger instruments, like a bass, like that standing bass. That has that produces very low notes. In the horn section, you have like trombones are like very long, large instruments. They produce lower notes. You could also decrease the wavelength, make it shorter. And what that would do is if you divide by a smaller number, you get a bigger one. So that would increase the frequency, which, remember, would increase the note. So think of small instruments, flutes, violins, things you can hold in your hand. Those have very small waves because they're tiny, and they produce high notes. So that's one thing that we can do to change pitch, is we can change the wavelength of the wave. We can change basically the length of the instrument. Okay, increasing velocity. So what you can do here is you can't change the speed of sound in air without changing the air itself. But you can change the nature of the instrument, and that would affect like how fast the waves move through the instrument. A nice example of that is a guitar. When you tighten the little knobs at the top of the guitar to tune it, you change how fast the wave moves through the string. And if you can make them move very fast, if you increase the speed, well, look on the top here. If you make this number larger, then you increase the frequency. So the higher notes on like a string instrument, like a guitar, violin, and stuff like that, are the ones where the sound moves very quickly through it. Decreasing speed, so the ones where sound moves a little bit slower would produce your lower notes. So this decrease frequency. And again, basically, if you have a smaller number on top of our fraction, you'll get a smaller frequency. So these are the things we can do to an instrument to change the frequency that it produces, to change the note that it produces. So look at a couple examples here. We'll start with some wind instruments, and then we'll do the string instruments, and that's all the instrument types that I know. With wind instruments, the sound wave is traveling through air. So all wind instruments are basically some sort of tube, maybe shaped weird, like, a trombone or a trumpet or something like that, or maybe like just straight like a clarinet. So that's all it is. So what's the speed of sound in air? Again, remember, it is 340 meters per second. Since it's traveling through air, we cannot change the speed of sound in the air. So what can we change, though, is we can change the wavelength. We can make it longer or shorter. Nice example here. When you press down on the keys of a flute or clarinet or trumpet, so the keys are like these little guys that you would press down on, you effectively make the instrument longer. Basically, when there's holes that are open, the sound can escape, and it's like a short tube then, because it ends there. But if you cover those holes, then the sound has to keep going, and you have a longer wavelength. So when you press down, the instrument gets longer, which increases the wavelength of the sound wave. What effect does this have on the frequency or pitch? So I don't know anything about playing these instruments, but I know that if you make the instrument longer, so if you press down on the keys, longer wavelength, we said earlier, is increasing the wavelength, and it would decrease the frequency. So it would decrease at the frequency, and you get a lower. Man, this is not going well for me today. Pitch. Okay, and that's how you would produce like a lower note if you wanted to do that. Trombone, they're these guys, and if you've never seen them played, like basically you take this extension part here, and you just kind of move it back and forth. And what that does is it makes the instrument longer or shorter. So you see how the sound has to travel all the way to the end, and then like all the way back, and then all the way out. If you retract this part right here, then it doesn't have to travel as far. It would maybe only have to travel this far. And that's how you change the wavelength. So if you extend the trombone, you make it longer. What would happen to the pitch of the sound it makes? Alright, well, if you make it longer, you increase the wavelength, which would, it looks like decreases the frequency. So that would decrease the frequency, and you'd have a lower pitch. So that's how you would produce a lower note. And then to increase the pitch, you would make it shorter again. If you unwrap the trumpet, it would be 1.3 meters in length. So basically, this trumpet, see how it's all like wound back and forth on itself? It's about 1.3 meters. Determine the frequency a trumpet will give you if no keys were pressed at this length. So by pressing these keys, you kind of change its length. But if you just leave it at this length, we're going to calculate the frequency. And if we're calculating, we'll use an equation. F equals V over lambda. Again, we know the speed of sound, it's 340. And we know that because I told you that. That's basically what it comes down to. And then the wavelength we said is 1.3 meters. So let's figure out what this would give us. 340 divided by 1.5. I'm sorry, divided by 1.3. I got 261.5. And so that frequency is, corresponds with a certain note that you would hear. Okay, so that's our wind instruments. Let's talk about string instruments, like the changes you make to them. So the waves generated in the string or the surface of a drum do not have to travel the speed of sound in air, although it is worth mentioning that the sound wave generated do travel at the speed of air. So what I mean by that is, when you pluck a guitar string, you make waves in the guitar string. And those can travel at different speeds. Like the guitar string can vibrate at whatever speed it wants. But once those sound waves enter the air, they all travel at the 340. But again, we can manipulate the strings themselves to change how fast they vibrate. So when you tighten a guitar string to tune it, you make the vibrations travel faster through the string. What will this do? So let's go here. Traveling faster means we increased the velocity, which it looks like will increase the frequency. So it increases the frequency, which gives you a higher pitch. So if you've ever played a string instrument, a guitar, violin, cello, anything like that, you know that when you tighten the strings, like what you hear is a higher pitch. And the reason for that is basically you're making the sound travel faster through the string. When you place your fingers on a guitar, you make the length of the string shorter, from the bottom up until your finger. What does this do to the pitch? So, this is a guitar string, right? It's this whole length right here. But, let's say you put your finger on it, and you put your finger like here. What you're basically doing then is you're changing the length of the string. So it's no longer the whole thing, but it only vibrates from here to here, which is shorter. So you're changing the wavelength. When you do that, what did I say we're doing? We made it shorter. So what does that do to the pitch? Well, shorter wave, so we decrease the wavelength. It sounds like it'll increase the frequency. An increase in frequency means, let's just jump to higher pitch. Cool. A piano has different strings at different lengths. So if you look at like a grand piano, something like this, see how it goes from like being very long in this section to very short in this section. And that's because there's just a bunch of strings inside, and when you hit the keys, it like bashes those strings and produces a note. Which side of the piano would you expect to have the lower pitch notes, and why? So I would say it should be the longer side. And the reason for that is because they'll have a longer wavelength. And we said the longer wavelength up here, again, longer wavelength, of course, increasing wavelength decreases the frequency. And so these will be your low notes if you hit these keys, and these will be your high notes if you hit those keys. Alright, a xylophone has these little different things. You hit them, they produce a note. Which produces the lower notes, and again, the longer ones. For the same reason. Because they have a longer wavelength, which just produces lower notes. Last one, a calculation. Vibrations travel through a certain violin string at 40 meters per second. If you hold your finger to change the string's length to 0.15 meters, what would the frequency that the violin produces? Well, we have an equation for that. We used it once before. We're going to use it again. V equals... I'm sorry, ooh, all messed up here. No, F equals V over lambda, which remember is just the way that what we use for wavelength. Okay, V is, we said in the problem, 40 meters per second. The wavelength is 0.15 meters. So we're going to divide 40 by 0.15. And when I did that, I got 266.67 hertz. So by doing this, you're causing that string to vibrate back and forth 266 times in 1 second. Those vibrations reach your ear, and that's the note that you hear. So today I just wanted you to sort of take some of the ideas we talked about last time and connect them to like a thing that you hear and notice, which would be these different notes.